Hi everybody. So in this video, we're going to look at solving second order differential equations numerically. So in the first example, I'm going to show you how to derive this equation. And then in the next example, we're going to use this equation to solve the second order differential equation. If you want to work along with me, you can download a copy of a PDF from my website. I'll leave a link in the description. So to derive this equation, we need to find the rate of change of a gradient. This is the d squared y over dx squared. And we need to find it of this curve. So the rate of change of a gradient will be the difference between the gradient of this, which is dy over dx, at this point, x0, minus the gradient of this line segment, which is dy over dx, at x is -1. So to find the difference between these two gradients, we have d squared y over dx squared at the point x0. This will be dy by dx at the point x0 minus dy by dx at the previous x value, x -1. This is divided by the change in x, which we've been told here is h. Now we can write our numerator in terms of y's. Well, the change in y at x0 will be y1 minus y0 over the change in x minus this one, which is y0 minus y -1 over the change in x, all divided by h. Now we've got two fractions with the same denominators, so we can put our numerator together. We've got y1 minus y0 minus this y0, and then the negative here will give us a positive y subscript -1 over h. But because we're dividing by h here and again here, this will just be over h squared. So d squared y over dx squared at the point x0 will be equal to the y1 minus 2y0 plus y -1 all over h squared. Say you wanted to work out future y values. Well, we can generalize this using an iteration formula. If we have xo as our base, our current iteration, then d squared y over dx squared at our current iteration n will be approximately, should have said this should be approximately here, will be approximately the next iteration, so yn plus 1 minus 2. This yo is our current iteration, so yn plus the previous iteration, so yn minus 1, all over h squared. This is the equation we need to solve second order differential equations numerically. In the next question, I'm going to show you how we use this. So in this exam style question, we're given that the initial gradient is y1 minus y0 over h. This is Euler's original equation. Then we're given the approximation for the second derivative. We've been asked to work out y1, y2, and y3 when we're given the second derivative here. We're also told that the curve passes through 0, 1, the initial gradient is 1, and that we've got a step length of 0.1. The first thing that we need to do is we need to create a table. We've got our iteration, n. We've got the x value at that iteration, the y value, the gradient and the second derivative. So initially, when n is 0, we're told that x is 0 and y is 1, and that the initial gradient is also 1. Well, we can work out the second derivative using this equation. So d squared y over dx squared, when n is 0, we'll substitute in our x and our y value from the 0 and the 1. So 3 lots of 0 minus the 1 squared, and this will give us negative 1. So I'll put this into our table here. And then when n is 1, and then because h is 0.1, x will be 0 plus h, so 0.1. And then we need to think about y1. Then to work out y1, we need y negative 1, but we don't have this, so we can't use the second derivative. But what we can do is use the first derivative, because we've got the initial gradient of 1. This will become 1. This will be approximately y1, which we're trying to find, minus the initial y, which is 1, over h. To solve this, we'll move a 0.1 to the left-hand side and add 1 to both. So y1 will be 1.1. Now we've got x and y, we can work out the second derivative. So d squared y or dx squared, in our first iteration, will be 3 lots of the x, which is 0.1, minus the y, which is 1.1 squared. And this will give us negative 0.91. I'll put that into our table. Moving on, when n is 2, we know x will now be 0.2. And then to work out y2, we need to use our iteration formula. If we make this term y2, then the n value must be 1. For 1 plus 1 would make the 2. So we're looking at the second derivative when n is 1. We just work this out as negative 0.91. And we have our y2 term minus 2 lots of yn, and n is 1. So we've got the 1.1 plus the third term, 1 minus 1 is 0. So we want the 1 here, y0, all divided by the 0.1 squared. We can move the 0.1 squared to the left-hand side. We'll add this term and subtract that term, and we get y2 as 1.1909. So I'll put this into our table. Okay, so we've got x2 and we've got y2. Now we can work out the second derivative. So d squared y over dx squared. And the second iteration will be 3 lots of our x value minus the y squared. When we work this out, we get negative 0.8182. So again, we'll put this into our table. But finally, to work out y3, if we go back to our iteration formula, we want this term to be y3. So n must be 2. We will take away 2 lots of y2 plus 2 take away 1, y1. And this term will be the negative 0.8182. This will be approximately y3 minus 2 lots of y2, which is this one, plus the previous y value, all divided by the 0.1 squared. We'll move the 0.1 and the other terms to the left-hand side, and y3 will give us 1.2736. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link in the description below.